So the goal today is to do the second part of the week, the second part of the course. Essentially, we were looking at 543 on the torus. Okay, so the functional now, essentially, we are interested in, depending on this control. I go a bit faster, okay? So this is in L2 of space-time, and then you average, okay? This was the initial point, so lambda is the set, and then you want to renormalize. You have you want you want to understand the variational problem for this process, and this is Wt plus Zt now to the power 4, remember, and then this was the weak renormalization, so always you construct this very specific polynomial whose coefficients are certain covariants of this Gaussian field, and remember somehow Wt behaves like some regularization of the Gaussian free field, okay? So GFF. So this was thing. And when t goes to infinity, this goes to 1. So you get the GFF, okay? But otherwise, this is moot. And then the novelty is that this is not enough here. You have to subtract lower. So there will be other divergences. So if you try to study the model like this, we will see actually. This will play a role because at some point we are studying this object and we create objects which are constant, which goes to infinity. Okay, so they have to be removed in some way or another. And the goal is to use this term to do it. And there will be also a constant because I can always shift the potential by a constant. So this is because you normalize the measure. Okay, so you have the right to do that. There are these terms, and then there is always the energy, and here is just the L2 norm of U. Okay, so this is the entropic term, L2T, L2X. Okay, and all this, so U has to be adapted in the space, and then we want to understand this problem. And okay, the goal, the logic is the same. Okay, you want to minimize this quantity, and then we have good guys, as always. So this one at the 4 power of Z, and all the other are the bad guys. Okay, the game didn't change. Just now it become tougher because if now you consider, remember that this symbol is just the weak power of W. Okay, and then if depend on T, this is the weak power of Wt, and a property I didn't prove, but these are martingales. Okay, so if you construct this. You see, this was my interest in having a family which is a martingale. We really, up to now, we never really used this property, but I have to do some Ito calculus, so I want this object to be martingales. So somehow the weak renormalization is what is exactly the correction. You see, Wt is a martingale. The power of a martingale are semi-martingale, but the weak power is exactly coincide with the process to construct a martingale out of this, okay? And remember, so the regularities, again, just to have in mind, I think somebody told me it's difficult to imagine this regularity, but you have to keep in mind these numbers, so W1 W1 infinity if you want, so when you converge, this object will belong to C minus 1 half kappa, minus kappa, and W2 belongs to C minus 1 minus kappa. W3 does not exist at infinity. And you can also interpret this behavior by saying, if I look at Wt and I take L infinity norm, it will grow like what you expect. Okay, so another way to say so is imagine that if instead of looking at them as a distribution, I take a regularization and look them as L infinity function, then this diverge with a certain, this will behave like 1R plus kappa. Okay, it's exactly a similar statement. It's not equivalent, but it's not very far, and you can convert, essentially you can understand the behavior of distribution by regularizing and see how fast they diverge in some given function space. Okay, this was our problem. I will go a bit, so I will just remind you, so the first The 4 power of W, we didn't care because we average it to 0, and it does not depend on the control, so it will always average to 0. The first term we have to care about was this. And for this, we did Ito calculus. So we wrote it as the integral between 0 and t of some j. So j, remember, I write it here, another thing. Yeah, so let's do this. Let me put here another. So no, they asked me not to write too small. So let me. Okay, so let me write it here. So zt. It was, so just to remember what is z. Z is the integral of some operator multiplied u, and this operator was like the inverse of the Laplacian 1/2, so increase the regularity by 1, and then some localization. This localizes the frequencies around S, okay? So you are adding pieces little by little. This is like Lévy, if you want. No, you add pieces according to some scales, little by little, and this is more or less some kind of orthogonal. In L2 would be almost orthogonal sum, okay? You have to imagine that here you are summing pieces in frequency, and so you control each piece. And you see there is a lot of redundancy in U, because essentially everything depends on Z, what Z does, but if you modify U at some scales, at the wrong time, it does not care, because that operator projects out, but we don't care about that. So JS was this. When essentially I do Ito formula, this is a martingale, and essentially there will be a martingale term coming from the derivative of this. There is no correction term because this is a bounded variation. The derivative of this gives you Ju, and you put J on the other side because it's self-adjoint and you have a space integral, so you end up with the J applied to Ws, and then we add Us, and then I add ds, okay? And then I put this together with 1/2, well, the integral from 0 to infinity of the norm of Us in the space variable. And so here you will have, so I do a bit faster, okay? So I have ds, I can do up to infinity. Here it works only for s less than t. And then essentially this term plus that, so all this, you can rewrite as this. Let me write it in this way, plus us us. Well, you can rewrite as this squared, okay? So this contains u squared is here, is the double product, so let's say 1/2, which is what you obtain from that, okay? I go a bit faster. This is the computation we did yesterday. And then there is another term. There is a term which depends only on w, so some function only of w, okay? Plus a martingale, okay? So this function of w, which is essentially this object square, you take the average and you remove it with delta, and the martingale is 0, okay? So the martingale with the expectation is 0, and this term goes into delta, okay? The average of this term goes into delta, so we are fine. Okay? So we end up with this, and then the first idea, which Justin was skeptical about, but I showed you that it's working, is to put this, is to define a new object as this difference. Okay, essentially what I'm doing is that I'm calling this Ws, and then but psychology, so let's say one way useful for me to think about this, then any other equivalent mathematical interpretation, it's correct. Is to think that now I don't want to control u, I want u to cancel this, so I have to fix a part of u, which is this. And I still leave some freedom because I want to control still this process, okay? So essentially this is the first idea, is that I want to shift my control. I don't want to control U. I want to control W, and there is a one-to-one relation so far between the two. And and this will become, you see, then the size of this object, essentially, I interpret it as the L2 norm of W. Okay, so W become a new control, and I remove the L2 norm of U. Okay, this is the idea. The idea I'm using is that this object can be very negative, but I can make this object always compensate this negativity. Okay, so they cancel, and they leave a finite quantity, which is the L2 norm of W. Okay, so this is done. Okay, so this we fix, and then we go on. So keep in mind that this thing. Maybe I will try not to erase, but let's see. And now we are looking at the next term. So maybe you have a question about this part. You had all the night to think about it. Okay. The next term will be tougher. Okay. So this was the easy part. This is just algebra. I didn't do anything. Ito formula plus algebra. Here we have to work harder. So why I'm worried about this term? Well, now I'm worried about more terms, because now essentially, okay, let's update our Z. So you see at the beginning, Z, so U was L2, and essentially by that formula, Z is the integral of U, and then you have the Laplacian, so you gain one regularity in time and one regularity in space, so it's in H11. Integrability stay in L2, okay? So Z usually it's H11, until the end, because this is this object which controls the regularity of Z. But now we traded that object to control that, so we have to pay a price. Is that is only W that is in L2. Now this is L2. And U will not be in L2, essentially because this object diverges. Okay, so let's do a rough computation. What is the size of this object? The size of this object is essentially S. So W3 diverges as 3. You see, every power of W give you time to the power 1/2. Okay, so it's easy. It's like computation. This diverges at least something like this. Okay, this is W in L infinity. Let's say I measure them in L infinity. And J gains you 1. So this goes like 1/2. Okay, so this object is growing up. Okay, so it's not, does not want to be integrable in time, certainly, okay? So this object will not be, if you accept that this is in L2, this is certainly not in L2, so U will not be in L2, and Z will not be in H1, okay? So what is the regularity of Z? So let's write ZT now, it's minus the integral of this object, and you see, let's say T, and then here you put, you integrate until big T, JS, WS cube. Sorry, JS squared, because I have a J only in the formula which links Z with U. And then you have, well, this is now a contribution which looks like above. Okay. So this is now in H1 time H1 space. And this is like the regularity that Z had before, but this is a new object. I give him a name. It's like I call it W3 with the parentheses to know that it's some kind of integral or linear transformation of W3. And this up to T, and this object now with which regularity has. Sorry, okay, this computation I did it. So the size of, sorry, so the size of this object, I removed it. Okay, so this is S to the minus 1 you gain, but of course this object is this time derivative of something, so give you a power 1 over S. Okay, it's not important. Essentially, this object has to cancel the integral, otherwise the integral will give you another power of time. So this object go like S to the minus 2, essentially. If you want to understand the size of J, one power comes from this, because this is concentrated around the scales, and the other power is because sigma is the time derivative of a cutoff function. So it goes, if you compute it, it goes like 1 over S. So here was this minus 1, but you see, you lose the 1 as soon as you integrate. So this object is of size T1 half plus a cap. No, sorry. it's not. It's better, okay? Sorry, this was, okay, let me compute it. Let's see what is the size of this object. Actually, if you do the computation like this is integrable because this diverges like 3/2, and here you gain 2 power from the Laplacian, and essentially, okay, sigma behaves in that way anyway. You don't gain 2 power of sigma, essentially. Essentially, this is like a orthogonal sum. So this you can disregard this integration, okay, because you're summing orthogonal components. So essentially, this is minus 3/2, and you gain 2. So this will go, a priori, will converge like 1/2, but the meaning would be that this object is uniformly, so let me write it in this way. This object belongs in a uniform way to C 1/2 minus kappa. Yeah. Okay, so the end, again, this object is like doing an orthogonal sum, yeah?
If you apply once time the GS, it's the same thing as applying it 2 times?
Because I said something which is improper. So, I mean, it depends what does it mean, this. So it's a rough. So the point of sigma, you have to remember that sigma, it's concentrating, and it's the derivative of something else. Okay, so what happens here is that this sigma will take care of this time integral. Then you have to do in the right way, okay? I agree that it's not very nice written in this way, okay? But let's say this is the result, okay? I mean, again, I don't want to, yeah?
So in ZT, we are fixing capital T, right? Are the small t and capital T different?
So I integrate this object. So this you have for every t. But this object, you see, modify u only when the scales are smaller than big T. So you get this contribution only up to big T. Yeah. Big T is fixed. And after big T is constant because this contribution. Big T is the regularization. It's fixed forever. Now I'm doing certain operations. Yeah. And my aim is to get something where I can remove big T. Okay, so far I cannot. Yeah, okay, here I cannot because this product of regularity does not match to what I did in 2 dimension, which I removed big T and I went already to infinity. I didn't do any cutoff, will not work here. So I have to be more careful. I have to keep the cutoff, do some transformation. So, but you see, the cutoff will remain only in a piece like this and it will disappear later. Okay, so if you look at this process, what I mean is that you can get estimate uniformly in this space because if you do the Little-Pally blocks, they will pick up certain range of frequency. The time integral will be of size 1, essentially, in every Little-Pally blocks, thanks to sigma. And you see, you gain the Laplacian, and you lose 3/2. Okay, so you gain 1/2. So this object, the Little-Pally block of this object, I can write down, but exercise for you. You have the definition of all the objects. Right now, I mean, somehow all this computation, they seem complicated, but I feel if you really just don't try to look in the books, but try to think about the definition we gave and try to do operation with Little-Pally blocks, is actually quite elementary theory. And once in a while, you have to look into the book. Okay? And it's really an object which you can manipulate very easily. Believe me, because I mean, I didn't know anything of this before starting, so it's not that you have to study 30 years. You look at the definition, and it do what it's supposed to do. There are no tricky parts, okay? And when you don't know how to estimate, you look in the book, how you estimate this norm of the Little-Pally blocks, and you see the proof is elementary, you learn a new proof, and you're done, okay? But technically, they do what you expect it to do. When you take a Little-Pally block, the sigma here will make so that S should be in the dyadic range of the Little-Pally block. And then, and then every object has an estimate in that range. Okay, so at the end of the day, exercise for you, you should be able to prove an equality like this, okay? At least I have an idea how to prove it, okay? And of WS, you use L infinity estimates, okay? You see, you use only the Little-Pally block to restrict this integration in a range, and then you can use L infinity on everything. You don't care anymore of distributions, okay? This is the idea of, let me write so that I see that, let me write something like this. Essentially the L infinity norm of this is bounded by what? By the integral between 2I and 2I plus 1 ds, and then you have the norm of JS, sorry, the little, yeah, once you have used the little polyblock to restrict the norm, you can forget about the little polyblock. And the size of this object is s to the minus 2 and s to the minus 1 from the sigma square, okay? Sorry. Yeah, maybe I was improper here, okay? But anyway, I need this, okay? This is the return. There is the computation in the note, so I think I did it for that, because this is the derivative of the rho, so this object is the one which get the 1/2. And this goes like s to the 3/2, okay? But all this is concentrated in this frequency, so here you get 2 to the I, 3/2, minus 2, and then you get, so this goes like minus 1/2 I, and you have this, okay. Okay, so that, sorry, this is not Z, it's W3. Okay, so now Z, you see Z is the sum of something in C1/2 minus plus something in H1. Okay, so this is W3, and this is this process. Let me give him a name. This is, we call it KT. Okay. So Z is the sum of W3 plus K, or minus W3 plus KT. Okay, and they have uniform estimate in these spaces. Okay, so this belongs to C1/2 minus, and this belongs to H1. So you see, we paid a price, okay, to do this compensation. Z is not anymore in H1 like it was in 2 dimensions, for example, because we were controlling the entropy. Z will be in regularity, will have regularity 1/2. You have a piece with less regularity but more integrability, and a piece with more regularity but less integrability, okay? This is coming from the fact that now the idea is that you want to put W in a L22, okay? Because you have this quantity. Next piece, okay? So let's look at the next piece now that we have this. So next piece is this. Actually, now even okay, let's look at this. Even the other term will create problem, but this creates really a lot of problem. W2, remember, is in C minus 1 minus kappa. And now Z square, essentially the most irregular piece is this. So it's a regularity 1/2, okay? The square of something holder, it's holder of the same regularity. Okay, so you see that here we miss a lot of regularity. Still, we miss a lot, is minus 1. And this is only 1/2, okay? And the square of this is the same. This was a scale T. Okay, so we have to work a bit harder. And now I need a tool. Now I need a tool. So to handle this term, I need some better tricks. And I will introduce it now. So I cannot proceed like in that case because, well, I want to proceed like here. So a priori, I want to use Ito formula. So let's try to do it, okay? Let's try. If I use Ito formula, let's see, okay? I learned a trick. I try to use it again. This is the integral. If I do from 0, W is 0, so there is no other contribution, okay? But there is no reason to arrive to 0. You can stop anywhere if you like, just a finite. If T is going to infinity, so the only things you care is to get something which looks finite. So let's try to use the same trick. I do the Ito formula. How does it look like? You will have, and again, okay, when you differentiate this, you get a martingale, which will be 0. I will ignore it. So the only term you care about is when you differentiate that. So this is the S square, and then you have maybe 2. S, and okay, so you differentiate this, you get ZS, and then the derivative of ZS, which is JU, let's write it in this way. Okay, if you try to do that computation, and then the S. Okay, so you get a term like this plus things plus a martingale. Okay, you know. And again, here you can put this on the other side, so because you have the space integral, so you write this as 2js. So let me rewrite in this way. Maybe you want to rewrite this as 2js w2s zs. This is all computed time us. Okay. Because this integral is the L2 norm, so you can move this, looking at this as a scalar product between these two things. But now you see, you want to do a shift. Now I would like to repeat the same argument, okay? It's the same structure, so I try, well, I have to do a bit more because now I don't have U anymore, okay? But this is easy because essentially you write U as this term plus that, and you apply the completion of the square here. Okay, this is what we wanted to do. But this term, it's still very complicated, and now contains Z. So you see, if you try to write, now it's not an explicit term anymore. It's something which depends on what you're trying to control. It will give us an equation. And if you try to go on in this way, you will hit some problem later, so it's better to solve the problem now. I cannot, I mean, I don't trust me that here you want to solve the problem that is this object, you're trying to remove too many things. You don't want to remove all these objects because you don't need and create problem later. You are too ambitious here, you cannot do everything. And here we will need a new object, which is called paraproduct. So I need okay, so here we are. I need now, maybe if you're not interested in this problem by itself, so now I need a technology which was invented for a different purpose, but actually was invented for this purpose. So here now you have a choice. You have to understand better you have to understand better what happens here, and what is missing somehow is that we have a good understanding of the regularity theory. We know Bezos spaces, but it's a theory of linear spaces. Okay, every theory of distribution is a linear theory, and what is missing, it's how you handle nonlinear operation. Okay, here you're multiplying two functions, and you want to understand more in detail what happens. Okay, we know already that you cannot multiply functions if the sum of the regularity does not agree, but we don't really understand very well why. Okay, so this tool, it's one way to understand exactly what happens when you try to do nonlinear operation on distributions. Okay, so it can apply to many contexts. And here you have the choice. You can use paraproduct, or if you like regularity structure, maybe you can try to use regularity structure. This is independent of the variational approach. There are two orthogonal tools, and you use whatever fits to you if you know regularity structures. But certainly you have to do something. So in the context of Bezos spaces, paraproduct is a natural way to do. So let's try to understand here. So I need a parenthesis. I need to explain to you what is a paraproduct. So imagine you multiply two distributions. Okay, so this is what we want to understand, because we want to single out the part here which will give us problem, and just leave around all the other parts. Okay, so I don't want, essentially, I want to pre-process this object so that when I arrive here, it's easier to remove what I need. So I need to understand the products in this operation better. Okay, so I start to look at a product, and now if you decompose a product in little Pauli blocks, so this could be distribution, but certainly each block is a function, so there is no problem in multiplying. The problem becomes how you handle the double sum, okay? In this sum, there are three pieces, so I will go a bit fast, but let's say there are pieces where E is less than J, and then there are pieces where E is essentially J, and they are the other diagonal with E is bigger than J, okay? Remember, these are dyadic blocks, okay? So the point, so why I separate in this way? The point is that if you multiply, if you are in the regime where I is smaller than J, let's say this symbol means that I is less or equal J plus a universal constant or minus a universal constant. So you take a thick diagonal and you look at the two parts. How thick is the diagonal depends exactly what is your definition of the Liouville-Pauli decomposition, but there is always a way to do it. Because let's forget about this. When you take I less than J, you are multiplying a function. You see, which this function oscillate way less than that function, okay? Because these are dyadic decomposition, okay? So if this has oscillation at scale 1, this has oscillation at scale maybe 8 or 16, okay? So, and then if you understand how trigonometric function sums, okay, the sum of the the product become the sum of the frequency. Try to multiply sinus and cosinus, you have this addition formula. So the frequencies, this dyadic annulus is just modified by the dyadic annulus of that. But the point is that if you take this dyadic decomposition, the support of this thing, so let's write it in this way. The support of the Fourier transform of this guy is contained in some dyadic annulus, maybe a little bit, but always at the bigger scale. Okay, so essentially here you have a dyadic annulus, and you are convolving it with another dyadic annulus, which is much smaller. So every point just become a bit spread out, but if you choose the difference of the two scale large enough, this will be still a new dyadic annulus, maybe a bit bigger. Okay, you can fit the thing. Okay, it's geometry of the support of the product of two functions which have bounded support in Fourier. Because this is very important. What you don't know, so what is the difference is that instead, if the frequencies are the same, this will not happen. Okay, if you multiply two signs with the same frequency, they can interfere and give you a constant, okay? Because the frequency sum, and you can get sum or subtract, and you can get a constant. So this is only supported. So the support of the Fourier transform is only, the only hope you have is that it's in a ball, okay? Certainly it cannot be very large, but you cannot have an annulus, and this with some ball, okay, some ball much of this size. Okay, this was make difference, these three pieces, and then you write the product as three pieces. Is not, they're all good in some sense, so they're not, but okay, this is maybe is ugly, but this is good, okay, certainly. And then you have the other one, and it's asymmetric, no, sorry, okay. So I use this strange symbol. Other people write something like this. Okay, depending on the paper, you use different notation. Okay.
Sorry, I don't understand why when I is approximately J, when the frequencies can be 0.
Yeah, it can be very small because the frequencies sum, but since you are summing two frequencies of the same size, they can cancel each other, and you get something very near to 0. Okay, think about well, sinus square of x, then you get, or cosinus square, then you get 2 plus whatever. Okay, you get a constant. And if they are very near, you get something which is unrelated. Okay, the point is, I think about you have to do this sum, and you look at the output of this sum, okay? So every piece coming from the middle, you don't have any control about where it's going to be in the product, okay? They can all accumulate at very low frequency, and it's an infinite sum, so you don't control it. The other two pieces are nice, okay? This object, the pieces around, so this is a double sum, okay, this is the problem, it's a double sum, but all the pieces essentially concentrate at the larger frequency, so you have a sum. So in particular, you see what you have to think about is that when you take the elitable Pauli, this is not true as I write, but it's the moral of the story. When you take the elitable Pauli block of the product, you don't know exactly what's going on with the elitable Pauli block, but if you take the elitable Pauli block of the paraproduct, okay, then you know that this object is concentrated on a dyadic annulus, so and here you are scanning all the dyadic annuli, so there are only finitely many of this block. Somehow, this block single out the frequency of this variable. Okay, so let me write in this way. You have to. This is not true, okay, but this is what happens in the proof, and this idea you have to have in mind. Essentially, this object more or less looks like the low frequency of f. So let's write it in this way, times the high frequencies of G. Okay, so this block picks up only the same frequency of G. While for the middle term, you don't have an idea, because what happens to be at frequency too high can come to larger frequencies. Okay, so essentially, if you do the same operation, if you do the same operation for the product, since the product lives in a ball, if the ball is too small, you don't see it, but you see all the large balls because they intersect your annulus. Okay, so these behave like the sum over J, let's say the sum over K bigger than I. Okay, they have to be big enough. But okay, here you have annuli, and imagine you intersect with your annulus. So small balls you don't see because they are inside my annulus, but at some point the ball become very large because I have to sum over all J in the product. And then I intersect that ball. Okay, so I see essentially all the blocks, all the product of things. They have the same index, more or less. Again, okay, these formula are heuristics. Okay, so keep them. They are false as they are written, but this is the idea you have to have in mind. So let me put a lot of symbols. Okay, this is not certainly is not. You cannot do proof with that, but it's the moral. This block will see only the oscillation of this, and then you multiply with all the smaller oscillation of f, okay? And this object see all the product of the similar oscillation of the two functions for all larger frequencies. Okay, so you see that they behave differently, okay? Because when these are always infinite sums in some sense, but then when you take little Pauli block, you cut here to a finite number of contribution, while here you still have infinitely many. This is the difference between these two quantities. And out of this awareness, you cook up very nice properties of this object. So I need various properties. So if you see this thing, they look very much like discrete martingales, okay? So look at this. This is the increment. In my mind, this looks very much like the increment of a stochastic integral is the increment of the integrand times the integrator, okay? And it's even adapted, okay? Because here you take all the things which come before. Okay, so the flavor of the theory of Bezos spaces has a lot to do with martingale, and in harmonic analysis, there is tight connection between martingale and analysis of this kind of spaces, okay? So you should, yeah, but think about this is the analytic equivalent of doing a stochastic integral, and this is the analytic equivalent of the quadratic variation in some sense, okay? And you know that is the diagonal piece in, so when you do, this is like multiplying to martingale, and then you get two stochastic integral and one quadratic variation, okay? It has the same flavor. It's not the same, has nothing to do, but there are many things which look very similar. So these are maybe, I don't know if you have intuition, I find very interesting. Okay, so the paraproduct oscillate like the function at a higher frequency, okay? And you can, more or less, you can treat the other function as a constant. That's what it gains to you. While this, you see now, if you want to estimate the base of regularity, if you believe in something like this, it's an exercise, okay? Because the base of regularity let's say I do for the C spaces, but the same theory is true for any Bezos spaces, so you just have to adjust the index. So if you want, let's say if this lives in C beta and this lives in C alpha, this paraproduct is always defined, okay, because there is no infinite sum, so you can always multiply things in this way. And this is the output regularity. You see who controls the output regularity. The size of the blocks is essentially the size of this term. And now you have to understand, so what is the size of this object? Well, if f is a function, this is bounded in I. If f is a distribution, this is growing, so it's contributing. So here you have to put what? Let's say, if alpha is positive or 0, then here you put beta, and this is controlled by f in C alpha and g in C beta. If alpha is negative, then of course this is of size proportional to beta, and this is of size proportional to alpha, because this is the size of the blocks grow geometrically. So this goes, this is if alpha is positive, and if alpha, let's say, here you have to put alpha plus beta. Okay, but you can do for any. Okay, so the regularity cannot be better than beta, but can be worse if you multiply with a distribution. But you can do the paraproduct of two distribution of arbitrary regularity, okay, because of this formula. Here it's more complicated, okay? Here you have to deal with an infinite sum. When you try to take L infinity norm of here, essentially you don't have any choice here. You have to pick up all the contribution. So this is called the resonant product, let's say. And this is paraproduct, okay? And the resonant product of two functions is bounded in the sum by the, let's say, by the regularity of the two functions, but only, this is true only if alpha p beta is positive, okay? Because you need to make this sum converge, okay? So this object has to decrease, cannot increase geometrically. Okay, so the sum of the regularity of the two functions. Okay, think about estimating this. This goes like 2 to the kappa alpha. This goes like 2 to the kappa minus alpha. This goes like 2 to the kappa minus beta. And if alpha plus beta is non-negative, this is increasing, is non-positive. This is increasing, and you cannot bound the sum. Okay, so it has to be strictly positive. 0, you cannot allow 0 either, because this sum will diverge logarithmically in that case. Okay? And there is no way, okay? It's not decreasing. You see, it's not a problem of the sum of, it's not a problem of the behavior on I. It's that you have, for every block, you have to infinite contribution, and they have to be small. So that's why, and this is the reason why the product is only well-defined, at least in the Bezos setting, is only well-defined in general when the regularity is positive, okay? Questions? I know that it's the last day, and this is not, we should do the lecture in the opposite. No, we start from the end, and then when we are at the end, no, at the beginning we are fresh, so we can do the difficult stuff, and then let's try to ask a question to make it slower, otherwise I go too fast. Behind. Felipe, I asked you a lot of questions. So yeah, sorry, I don't remember you.
So when I is approximately equal to j, when in this first decomposition, you say that the support of the Fourier transform is the goal.
Yeah.
But then you say you can represent the sum in these three parts, and this little pair block of the middle thing is the sum for big k.
Yeah. Well, because sure. You see, this says this product, this product is the sum of all the things at similar scale, okay? And each of them is in a ball, okay? So you are summing over balls, okay? sum over k, and the ball is of radius 2k, okay? Now, the little Pauli block, what it's doing is that it's projecting in a given annulus of radius 2j, okay? Means that the inner and the outer are of size 2j. So in this picture, if k is too small, your annulus is here. So you don't see the k small, but then when k become large, your product can be in a very large ball, because the sum of the two frequencies, you are summing two frequencies which are of order 2 to the k. And you have to attend that 2 to the k start to be bigger than 2 to the I. So you only sum the k bigger than I. Okay? So this is the little Pauli projector. It will look only what happens in this region. And your product of objects will just be something in this region, so you will not see it until k become very large, and then you start to be here, then you start to see something. But then even when k much larger, of course, is a ball, that's the problem, okay? When k can be much larger, you still see something in the annulus because you cannot exclude that it's a ball, okay? This will not happen here with an annulus, because when the annulus become very large, at some point, you never intersect a smaller annulus. But a ball, very large ball, will always intersect a smaller ball. And so you get all the contribution from all the big balls, but not the small, okay, certainly. And this gives you this is important, to remove the small ball is important to get this regularity, of course, because you want this. But you can do this estimate only if the sum is finite, so you need a condition to ensure that this sum is finite. This does not happen here because the product is in an annulus, and then a dyadic annulus intersect only finitely many other dyadic annulus, however you construct them, okay? The freedom you have to construct the little Pauli projector is to choose exactly how an annulus compare with another dyadic annulus. So it could be that one dyadic annulus intersect finitely many of other dyadic annuli. What you can do optimally is that it intersect the next neighbors, okay, but not anybody else. This can be done, but it's not very important, okay? And another important fact, for example, for your intuition, is that when your function is a sum of pieces on dyadic annuli, so you see, the important thing is not, essentially this product, since this product is supported in since these elements are supported on dyadic annuli, essentially what happens is that they always define a well-defined distribution, okay? So this sum, in the sense of distribution, is always well-defined, okay? Because essentially, if you test with a smooth test function, you will see only finitely many elements in the sum, because it intersects only finitely. Well, the proof goes like this, okay? Because somehow things that happen in different dyadic annuli looks like orthogonal, so you will never see a full sum. You will always see pieces. Okay, think about in L2 how you handle function with in Fourier transform. This is somehow some relaxation of the same kind of argument that you use in Fourier transform. Because you don't want, as we saw from Carlos' talk, you like to work in Sobolev spaces because they give you this Hilbert space structure, and here you keep just enough but you work in a more general setting. We have a friend going around. He does not like paraproduct, apparently. Okay. I need another element of the theory. Can you ask? Yeah, Felipe, you had a question. No? Okay, good. Now is an exercise for you. If you believe you understood, or if you want to understand, there is another property. Now if I take the integral, and of course we are on a torus, so the paraproduct I'm considering are those in the periodic domain. Okay. Okay, now you take the scalar product between a paraproduct and another function. Okay, so sorry, this is the usual product. Okay, so now you want to see this as an operation. This is a linear, a way to see a paraproduct, which is used in many also things, is that you see as a function, as a linear operator on the right argument. Okay, this is the right way to look at a paraproduct, because if f is a function, this operator it's a mapping between the same Besel space. Okay, you see here. Okay, if f is a function, you are just modulating a function and staying in the same space. Okay. Think about stochastic integral, think about martingale. If you have a martingale, you get another martingale. Okay, that's very nice way to think. So this is like a stochastic integral where this is the integrand and this is the integrate. No, the other way. Okay, this is the integrand and this is the integrate. And then you multiply with h. What I want to say is that, so in a product, you see, when you integrate like this, so the first property is that when you integrate like this is the same thing as taking this function and computing the resonant product, okay? Okay, again, okay, this product can be decomposed, but you see, all the paraproducts have the image in dyadic annuli, and when you integrate, you want to see what happens around the constant, okay? You're essentially taking the constant part of what you obtain. So every dyadic annulus will disappear if you integrate, because you're testing with the function 1, the Fourier series, and you only have the paraproduct, which can provide you constant terms, okay? This is like Parseval theorem, okay? When you multiply two functions, in Fourier space, you are just summing the square of the same coordinate, okay? It's an approximate version of Parseval theorem. And now, you see, now you want to understand something. Essentially, if f is constant, this is the resonant product of g and h, okay? And I told you that the paraproduct just give a modulation of g. So what you want to say is, that this is also the product. Yeah, I think I want to say something like this, okay, that this is the integral. Sorry, certainly I want to say that this is the integral of f times the resonant product, okay, but this will not be true, because everything is true up to, I mean, it's morally true, but you have a correction term. So how you express this in this context, you say that sorry, now I'm a bit puzzled by something. Let me think a moment. Yeah, you say that this is true up to a commutator. Sorry, now I'm a bit puzzled. I didn't want to do that. I'm making confusion between two different things. Okay, let me tell you another thing before, and then we think about that, okay? It's this thing, but I don't need the integral. So the first thing, okay, let me tell you various things. So the first thing I told you is the product of two functions you can, okay, reduce to the paraproduct. This is like some approximate version of Parseval. Say one, and then the second thing I want to tell you is, now, if you take, without integral, okay, if you take, this is certainly, it's an important thing to know, is what makes these things interesting and useful, because at this moment we just decompose a product in three pieces, but then you want to understand how these pieces can be manipulated, because otherwise we are. And this is the interesting thing, is that if you take a paraproduct and then you want to take the resonant product with another thing, because you are decomposed two products, then what you want to say is that this object is equal to, ideally you want to say that this object should be related to the paraproduct of, to the resonant product of these two functions, okay, because of this property. When you take the block of a paraproduct essentially is the block of G. And when you want to multiply the block of a function with another in the resonance sense, you multiply the blocks. So essentially, you want to say that the block of G multiplied by K is the resonant product of G and K. And then F should be somewhere in this formula, so I put it in front. But then, of course, this is morally true. And actually, this is false. So first time we try to prove this thing, you want to put the paraproduct here, but this is not going to work very well. So this worked very well somehow. But you have to pay a commutator. So this is true up to a commutator. So let's call it commutator, and which is a trilinear function of the three variables. So what makes it useful? Okay, this is algebra, in the sense you define the commutator as the difference of these two objects when they are well defined. And then what you want to say now is that the commutator exists when these two objects does not exist. Because remember that the resonant product has a condition on the label. Okay, you buy it, but you can use it only when this is satisfied. So you have to read the instructions, otherwise you break the product. And here now, imagine you have three regularities, alpha, beta, and gamma, okay? So these products and that product are defined, let's say alpha is positive. So a priori, these two objects are defined only when beta and gamma is positive. But then the commutator is okay when the sum of the three is positive. Okay, so this is what you gained, okay? So if you are in this condition, but beta plus gamma is negative, so this could be happen because alpha helps, okay? Then these two objects are comparable. Okay, they are not well defined both, but they are not well defined up to a well defined piece. Okay, so when you are here, you can always go there and pay a price. Okay. What does it mean not to be well defined? Remember, we have in our context it means we are working with smooth functions, so all the operations are allowed, but then when we want to take the limits, we will see real distributions, and so these two objects should diverge in the same way. Okay, this is what's written because this object, it's fine. Okay, this is one of the tools we are going to use. Okay, again, the right way to say it and how it's written, it's I define this trilinear function. Do you see it, or there is the blackboard? Is okay? We define this trilinear function as this difference is a commutator between two operations. And then this trilinear function can be extended continuously when these conditions are satisfied. Okay? Does it? Okay, you know this from stochastic calculus. Okay, the quadratic variation between a process and the stochastic integral is the integral of the quadratic variation of the integrators. Okay, you see, it's not novelty. I think everything more or less works similarly because at the end it looks like discrete martingale. So the argument is the proofs are very similar. Once you have a good intuition about how they behave, you set up the proof in a way that then it's easy to carry out. Okay? I need Okay, so now let's start to work out what we have to do with this. Yeah, there is a third operation. Yeah, let me add a third property maybe, just to mention it. So third property, this is, yeah, okay, I will not have time to enter all the details. So I think to me, I would be happy if you carry over from this last lecture like this thing. Maybe it's useful to you in something. So another property to understand how to use these things is, for example, I have a paraproduct, and I apply some Fourier multiplier to it. Okay, imagine I want to apply a J operator, some regularization operator, or even some, usually regularization operator. Okay, so what you want to say is that somehow is like, again, okay, the theme is always the same. You want to reason as this function is not there. Because somehow this function is just modulating a bit what G is doing, because it's perturbing the frequencies where G oscillates. So if this operator regularizes certain frequencies, it will regularize similarly. So you want to say that this is F paraproduct. No, this is a linear operator, so will never perturb very much the paraproduct decomposition. Okay, but so you want to say that this is like acting directly with G, because it's the block of this product are the block of G. And the size of this object maybe depends only on the blocks, because it's a multiplier. So you want to say that this is equal to that up to another commutator. Okay, okay, this depends on eta also, but somehow it's a bilinear function of the two things. And again, okay, what you expect is that somehow if you expect that these two objects to have the same regularity and the commutator to be more regular, because if the function is not there, the commutator is 0. Okay? So if the function has some regularity, you expect that this has the sum of the regularity. Okay? So essentially, this will have the regularity of, somehow this is more additional regularity coming from F. Okay, it's the same argument. Okay, it's the same argument. The commutator, F is a spectator in this quantity. Okay, if F is very regular, you don't care, because the regularity of the paraproduct is the regularity of G. But in the commutator, you see the regularity of F. Okay, so if F is regular, this object will be more regular than each of them by the regularity of F. Okay, and then you have lemma proposition 68 in the notes that quantify this. Okay. For example, let me give you an example. Okay, if you take the inverse Laplacian of F times G, and you want to estimate, let's say, in C alpha plus 2, so regularity of this minus something like this. In C alpha plus beta plus 2 is controlled by the regularity of F in C alpha and the regularity of G in C beta. Okay, this increased the regularity of 2. Okay, I wanted just to make concrete, otherwise I would have to introduce a notion of. So this increased regularity of 2, so G has regularity beta. So alpha it's positive, and beta can be any real number. For example, in this example, so G can be any distribution. You multiply with a positive distribution, you stay in the same space, you regularize by 2, and the difference, so this object has regularity beta plus 2, because F is not important in this, because this paraproduct has the regularity of G, then you increase by 2, so beta plus 2, but the difference between the two is better, you gain alpha. Okay, so this is the whole idea of paraproducts, is to isolate, to do a calculus of this object, and you do calculus up to smoother terms. Okay? So this is what you have to have in mind. Yeah, I think we are. Okay. Okay, then we have everything. So let's try. I think the only thing I will be able to do reasonably is to finish this computation. Okay. Let's try to do it. So we have, this is a tricky computation, so I think I didn't write it down in the best way I could. Maybe when I revise the notes, I will try to make it better. So let's try to go through it. So remember what we were looking at. Okay, we were looking at this term was W2 times Z square times scale T. Okay, I need to simplify the expression of this term. And essentially, inside this term there are various contributions. So let me see. Let me see how I want to write it. What I did in the notes is, first thing, I expand Z. So Z is like this W3 plus K, remember? So you expand this because there are various pieces. One piece is when you have W3 square, so you have things like this. This piece we don't care. Okay, this is a number. We remove it. Okay, so we don't care about this. But there are the other two pieces. So W2, and then you have W3 with the 2 maybe, and K. And then there is W2 K square. Okay, so you have these three pieces. So the first one, I can forget about it. It will be absorbed by delta, because when you take the average, it's just a number you can compute. So you can remove it by delta. This is good. Now I have to look at these two terms. Again, you want to keep 1K because you want to do, remember that so what we try to follow is the same strategy we were using here. Here we were doing a stochastic calculus where we generate U. And now somehow we want to have something times K so that we generate W and we can complete the square in the same way. Okay, so the idea is I want to keep 1K, but I need to operate on the others. So essentially these two terms, so you can follow page 58 of the notes if you want. And there is a bunch of things. Because now you expand these objects in paraproduct, okay? The difficulty is this object times that. So essentially you concentrate on this product, okay? Here you write K. That's it. Because you want to have something times K. So you want to leave a K, but you concentrate on this. This is one way to do it. It's the way we found. Maybe if it does not sound reasonable for you, try maybe different ways. But I guess at the end of the day, you end up, so you concentrate on these two products. And you want to isolate the difficult parts of these two products. Okay, so let's see. You have, in both objects, you have the paraproducts. Okay, so you have the paraproduct and the resonant product. Actually, here, you would have to do a bit differently. But let's say you have the paraproduct, the resonant product, and the other paraproduct. Okay, they behave differently. So you have to expand and check that you get the formula you have at page 58. So I will not do this computation because I will get it wrong. So you will have different contributions. So let me write it down, then we discuss what to do with them. You expand this object, but then you reconstruct Z, okay? Because you want a formula like this. So you have a term which is like this, which is coming from the paraproduct. So this is the paraproduct. Okay, so one of the paraproduct, you sum these two, will give you this. And then you have other pieces, so let's forget about the sign, just because it's not important in this argument. You will get the resonant term, so this is, unfortunately, you have to carry on. It's important with K. And then you have the other, so let's discuss all the terms together. You have the other paraproduct with K. And then you have other paraproducts. So I want to write them all to see what is the logic. yeah, and the last term is okay, let's write the last term is a commutator. So let's try to. Then there is another term which looks like this, okay, W2. Okay. Okay. Minus W2. This is the space integral. I didn't do any time differentiation yet, okay. Okay, so this is this term. Okay, it should be true that this is algebraic manipulation, okay, that this quantity, when you expand and you put things together, it should be that. Let's assume that it's true. You say, okay, when I wrote this, what I should see among these quantities, what orients you. They're put in this way. So what are the important terms? You have to keep in mind that we are doing all this job because this is irregular. So we have to keep an eye on this object because this is most irregular, and it does not like to see this person, okay? Because they cannot, this cannot win against that. So the first operation we did is that somehow put in less important z. So this object behaves like w. So I understand it very well. And then again, okay, this k outside play a role of spectator because I will have to do the completion of the square with that, okay, remember that. So this is an important term for us. It will be part of the drift. Again, keep in mind, sorry, let me cancel this. You have to keep in mind what you want to do at the end, okay? So at the end of the day, you want to complete the square. So we did it once. So we did it once for this term. So this will go in the drift term, okay? So this, when you complete the square, essentially the result is that this will finish in the drift term. So here, this will finish in the drift term. And this also, so now this is, I don't think I want to put it in the drift term, okay? Think about what's happening here. This is not a good term. I cannot keep it because this object has regularity -1, okay? A kappa regularity 1. So this is not good because this is always a bit less than -1, okay? So this I have to remove it, like here, okay? I had to remove it. So this has to be removed. Let's look at this. This is a bit better, okay? This is the resonant product. Of course, here is not well defined because this is -1. This is, I told you, is 1/2. Okay, we made this argument. This is the integral of W3. And this is a regularity 1, okay? So you see that this resonant product technically is not well defined. But because it's a stochastic object, I will study it, okay? And I will prove that it's well defined, okay? Actually, no, this diverges, sorry. This is going to prove our problem. Okay, this is an interesting object. It will be well defined, but I will have to subtract an infinite quantity, okay, from that. Well, you say how you see it, you don't see it, okay? But certainly it's not well defined, but you have hope that, okay, this is explicit, our polynomial of the Gaussian free field. I just compute them and see what's going on, okay? And here is the same pattern we use for the square, okay? The square is not well defined, but you subtract an infinite quantity and you are okay. Okay, so here we have hope, but we have to do a stochastic computation. So this is hope to handle it in some way, okay? Here you don't have hope because this is, you don't know this object. You cannot do any specific computation. You have to remove it from there. And then somehow, what is the hope here? Why I don't remove it? Because maybe I have to do something complicated to handle this, but certainly I can have hope that this is more regular than -1 because this is more regular and this is the resonant product. So if it's well defined, I have hope that this is regularity -1/2 and this is regularity 1. So this is, I can keep it there, okay? If I hope to make well-defined this product, okay? This is the logic. Then you say, I mean, it's not a proof, okay? You have, this is the way you try to go, and this will work up to a renormalization. Again, so now let's look at this term. Okay, this term is in good shape. Is more or less the moral is like this. You see, now we see the paraproducts, why I use them. So this is -1, this is 1/2, and here you have the paraproduct in the good direction. Okay, when it's always well-defined, a paraproduct, and it's the sum of the regularity because the low frequency function is negative regularity, okay? So altogether, this is of regularity -1/2, and this is of regularity 1. So here it's okay. This, you leave it there. You don't have to do anything for that. Okay, so we start to see some improvement for us. Okay, so maybe ask a question. So this is okay. Okay, this is, you see, it's good to have in the paraproduct, in the high frequency, a regular function, because this regularizes the other function. Okay, so this is a distribution regularity -1. You take the paraproduct with a function regularity 1/2. Think that always, when you take a block of this here, we will have a higher frequency block, which is very small, because this is a function. So this regularizes the blocks. Okay, all the blocks of W2 are made smaller by the contribution of that. So this overall, then you use the estimate for the paraproduct. This is well-defined, and there's regularity -1/2. And this is regularity 1, so we are in a good situation. Okay, we can hope to control it as we did in 2 dimensions. Okay, the product is well-defined, and we hope to have good estimate for that. Okay, so this is okay. This is also okay for the same reason, better reason, because K has regularity 1. Okay, so this is -1/2, this is 1, this is 1. So essentially, these two work together in this quantity. These two work together to beat here. You see, in a quantity like this, the square really don't work together, okay? Because you see, the regularity of a square is the regularity of the function. So here you have only one z to beat W, but in these two terms, you have two terms, the regularity of two terms, which sum up to beat this guy, okay? So these two terms are okay. So this is also okay, in the sense that I will have to estimate them like in 2 dimensions. So I will have to do work, but it is okay. Now you look at this term, and well, this term is not okay, because here you have a resonant product. This is -1, this is 1. And this resonant product has to be well-defined before multiplying by k, and here you don't meet the condition. Okay, so this could diverge, like this diverged. But here I have hope because it's explicit. Here I don't have any hope so far because this is not explicit, okay? But then magic happens because there is also this term which has a different problem, because here this product is well defined, but the regularity will be -1 because this does not add up in the regularity. This behaves like a constant when it's on this side, okay? In this situation it's good, it helps. In this situation it's just a spectator, is not doing anything. So this regularity of this is -1, regularity of this is 1. You get a problem in the resonant product here, okay? But now the magic happens is that there is another theorem that I didn't write down, of this commutator, that is the difference of these two quantities is a commutator between W and K. So the difference is well defined because you can use the sum of the 3 regularity. Okay, so this is regularity -1, this 1 and 1. So this is, you can sum the 3 regularity, which is positive. Okay, so you have to prove a lemma telling you that this is a different commutator, okay? I write all this commutator, but they are different. There are many of them, and the logic is always the same. So you write this quantity, you write down in Little-Wood-Paley block, and you see that they cancel. There are Little-Wood-Paley blocks which cancel and make so that this quantity can be estimated using the regularity of all 3 functions. Okay, the problem, I repeat it to make it clear, the problem you have in this so the problem you have at the beginning is that you cannot use the 2z you have, because each z has its own regularity, but in a product you only see the one of the 2 regularities, okay? But then when you decompose in paraproducts, there are terms in which you see the regularity of both functions, okay? And this is one of these terms, but you have to bring them together. Okay, so now the logic of this computation is that you can ignore, so far, we have Still difficult problem to solve because we have these two terms. Okay, so we have these two terms to take care of. At which time we finished? You remember? 15? Okay. I will skip unpleasant. Yeah, we have to manipulate this for the rigorous proof, but let's forget about it. I will not have time anyway to go into the estimate. So let's assume that, so you have, the pattern is I want to reduce a situation which is, then I can use the same logic in two dimensions. That is, I have object which I can hope to estimate with a good term. So let's assume this can be done. I have to handle these two terms now. Okay, all this term I can leave it there. But these two terms are still problematic. So let's look at this term. I told you this is a problematic because this product is not well defined, but essentially, if I do something, I have hope. So this will be left there. I will only have to do the trick for that one. So let's look at this term. This will show us the first renormalization, where I write. So I write maybe here. So we have two terms to care about. So I forget about this computation. I write the two terms. One is W2, ZK. I write it here, and I forget for the moment. Okay, and the other term I have to care about is W2, W3. Okay. Okay. Now, this, in some sense, the only problem is that I would have to study this stochastic object, like we studied like the powers of the Gaussian free field, and prove that it has some regularity, okay? The end product of this thing is that, so now you look at this object in the face, if you want, it's the product of two stochastic integrals. So you know already it's not a stochastic integral, it's not a weak product, okay? And what you get, so if you start to think a moment about this, so what will happen is that this object, if you subtract a constant time, yeah, let's do like this. Let's forget about the constant because I will have to track exactly the constant to make it work. But the moral is that now this object will not have a limit, but this object minus that one will have a limit. Okay, this is like the renormalization of the square. How you get, why there is one power of W? Think about the cube. The cube does not have a limit, but if you subtract a linear function, you create a Hermite polynomial, you have a limit. So here, what will happen is that somehow these two, so here you have like something which is quadratic. Here you have something which is cubic. Okay? So this is a quadratic Hermite polynomial. This is a cubic one. And you can multiply Hermite polynomial. The algebra of Hermite polynomial is closed because it's just a basis of polynomials, so you can express. And then you realize that the product of two Hermite polynomial is the Hermite polynomial of degree 5, and then there is an Hermite polynomial of degree 3, and an Hermite polynomial of degree 1. Okay, so you can express the product. So this is H2 times H3, and you multiply them, and you get H5 plus H3 plus H1. Yeah, you get the even one, the odd ones, because you have an odd function. And this one will give you good, well-defined random field. This one will give you well-defined random field. But this one comes with a constant in front, which is going to be infinite. Okay? This is like when you take the square, you have to subtract something. So if you subtract this quantity, which is the first order Hermite polynomial, you get a well-defined limit. Okay, so this is the logic. So you call this thing, you give it a name, you call it like the renormalized product. I think I define it in some, yeah, I try to have some notation. Okay, this is you define this object like this, okay? I find it cool, so I mean, I don't care what you think about it. And it's fit the purpose, okay? It's not systematic, so Aurélien will not like it because, of course, I'm not using multi-trees, but essentially you can do whatever. Okay? It's enough for us, okay? This is a simple problem. I'm not. So you define, this is a definition, and then you check that this random field is well defined, and that, so W2, okay, this strange object now exists, and it lives in, you see, inside there are various things, but I don't care. The only thing that I care is that here there is an infinite constant, so I subtract it. Okay, well, this is a computation you have to do, how you see it, because essentially the first order Hermite polynomial will come from the fact that you contract two legs, and this looks like when you do the square, this creates a problem in this problem, okay? Well, when you contract only one leg, there is no problem, okay? When you contract two legs, there is a loop, and loops give problem in this business, and gives infinite constants. Anyway, you don't care. I mean, this is, you can check by hand, even not knowing anything about Feynman diagrams. And you check that the higher order terms are usually more well behaved than the lower order terms. So the lower order term could diverge, and here only this one diverge, and you subtract it, and then you get a well-defined thing. And then what is the regularity? Well, it's -1, 1/2, and is what you expect is regularity -1 plus 1/2 minus 1/2. So it's still negative, but is better, okay? And now you're happy. Well, you're happy. So now this object, if you make this appear, will be okay, okay? So now you write this object as the integral of this renormalized product time k plus gamma t w t kt, okay? And if you did the things correctly, well, you can choose the gamma. You see, now this is going to infinity, okay? So gamma t essentially is going like, I think, log, no, I think it's going, sorry. No, gamma t is diverging, it's going like log t. Okay. So why I think it's log t, because think wt already goes like -1/2. So it's the same regularity of your object, so there is no additional divergence needed. So it's going like, but it's diverging like a log, okay? Okay, this one has to compute, but this is a fact, okay? And now, if you remember, I put in my potential exactly a term which was like w plus z, like we product square, okay? So inside here, there is a, now you have to expand the z, but essentially there is a term like this. There is w times k, okay, which come from wz when you expand the z. Z is a linear contribution, okay? So this correction term take care of that, okay? There is a part of that correction term which care of this, okay? If you choose the same gamma, that's the choice of gamma you have to do, okay? So this is renormalization. Okay, remember that I use only part of this. For example, there will be still, it remains a term like gamma t zt square. Okay, there is a term like this which comes from this potential. So I use it to cancel this term, but I still have to remember that there is another term, and this term will go to cancel another divergence, which is still not there, okay? And the magic is that it works. Okay, so I think now we are, I'm done with the time. I have 4 minutes, 3 minutes. Well, I think, okay, let me stop here because I don't want to exaggerate. Okay, I think I showed different things. Now you say, why this term is still there? So let me just tell you this rapidly. this term should be there to cancel something. So what is going to cancel? The point is that now I told you how to handle this. This term gives you a well-defined thing plus an infinite cost of which you remove, because you have the freedom to remove it. From the beginning, I left me this freedom. But then I have to treat this, okay? With this, you do the shift again. So for this term, you complete the square. We did it already, so we have just to redo. And then it means that now so now if you remember when you complete the square, you will add another term to you. So will be, so again, I have this is what I had before. And then I will get another contribution, which looks like the j of that, okay? This is now the same. So essentially, there will be a contribution which looks like this. And then there is okay, so this is what, this is what was Wt. I have to do a shift of Wt, so introduce L, name. And then I have this additional contribution, which is the completion of the square of this. When you complete the square, before I get a term which is like this to the square, now I get this term to the square. So you get a term which looks like gs w square z times gs w square z from the completion of the square. Okay, you get the square of the term you added. Okay, this is like before you get this, but we ignore it. Now we cannot, because there is z inside. I cannot just subtract. I don't know exactly what to subtract. I cannot take the average of this. And this object, you see, give me problem. First, I can put the resonant product in the middle because it's the scalar product of the two things. And now you see this is -1. This is -1. This regularize, but regularize only of 1. Okay, so this is 0 minus. This is 0 minus, so this product is not well defined yet. And now it's the same argument as we used here. Now you have to use all the things I told you about the paraproduct. That is, this thing can be put outside by using some commutators. Okay, will be there. It's okay because the regularity 1/2, and this product is barely a function. But now this product creates a problem. Now you are multiplying, like here, 2 Hermite polynomial. So this product is like the square of something. So it will give you a constant which diverge, plus something which is well defined. Okay, this gives you first order polynomial, but here you're making a product of 2 even polynomials, so like h2 times h2. So you get h4, h2, and h0, and this will diverge logarithmically. Okay, so you have to remove that. So you remove the constant, and this is exactly gamma zeta square, which you had somewhere, okay, which I had from here. Okay, it will correct this in the right way. Okay, you have to believe that it's going to work. Okay, let me finish here. Okay, thank you, I think. Yeah, no, stop. We had the question, I always forget. You start to clap too early. But we want to, maybe if you have, let me finish. Don't ask question, or if you want to ask question maybe, no? Yeah, yeah. Well, this is, it exists, a theory of paradifferential operator. This object existed in the literature because it's used in hyperbolic, it's used to extend the calculus of pseudo-differential operators. This is a infinity calculus. If you have limited regularity, you have to do paradifferential operators. Then it's a calculus of operator of limited regularity with a smoothing term. Yeah, only that. Okay, so let me say I don't have a list of open problems because there are very many open problems. I told you about uniqueness, but there are many things to do. So it's a very active field of research. It seems difficult, but I think the point is that we try to make this kind of thing easier because the model we are interested in are even more difficult. So you want to understand things better, make it easier. So I think there is space to make things easier. just is a new object, so we need some time to digest them and understand what are the better way to handle those objects. But I think it will continue to get easier and easier. Okay, so it's a good field of research. Okay, thank you to sticking with me until the end. Boris and Asen, thank you a lot. It was very pleasant for me to being around. Yeah, and goodbye. See you next year, maybe.